This conference will now be recorded.
Hello everyone. Today we are going to learn an important numerical technique to solve differential equations. So it's called Runge Kutta Method. Now I am a bit used to calling this Runge Kutta Method, but seems like the correct pronunciation, you can just check it on YouTube, is Runge Kutta. Okay, but it sounds funny to me. But anyway, so Runge Kutta is like it's the name of two German mathematicians, like two different names combined together. So that's about the name, and it's a very special numerical technique because it's going to give you some like accurate answers, like I mean fairly accurate answers. Okay, so let me remind you what we did under numerical techniques few weeks ago. The first numerical technique we learned was the Euler's method. Now, let me give you a brief idea about all the numerical methods, what happens in all the numerical methods in general. Okay, so let's say if you have this differential equation dy by dx equals to 2x with y0 equals to 0. Okay, now we can, if you want, we can directly calculate the answer by doing like a separation of variable or something like that. And here we have a c, substitute in the initial conditions, we get c equals 0. So the final answer to our initial value problem. Now all the numerical methods are defined for an initial value problem. You need a place to start, and that is yx equals x squared. Okay, now so if we draw this function, it will look like this. And let's create a table as well. So this is x and this is yx given by x squared. Okay, now for example, for 0 it's 0, which is given. Okay, y0 is given as 0, that's the place where we started. Then as we know the formula, we have this as 1, and this is 2, 3 gives 9, 4 gives 16, and so on. Okay, now what do we do in a numerical technique? So the idea of adopting a numerical technique mainly appears when you don't have a proper way of getting this analytical answer. These are called analytical answers because we had a good, like a precise method to calculate this yx, and this is the exact answer to this differential equation. But just suppose you did not know this method from here to here, because in most of the complicated differential equations that appear in our day-to-day like practical situations, we will not have this sort of a method. Okay, so we do not know this answer, right? Now in all the numerical techniques, what we do is we can still come up with x values, right? So it's basically something we define starting from the initial condition. And remember, we are dealing with initial value problems in numerical solvers. Okay, so we know a place to start. This is the starting x naught value, and we know the corresponding y naught for that starting point. That means we will have this first row. but not the others, because we don't have the formula now. Okay, but still we can come up with these x values, right? So we start from here, and we can come up with these x values like this: 1, 2, 3, 4, 5. Likewise, we can come up with those x values, and it is customary to position these x values with like an equidistance x values. Okay, so we extract out a set of x values with the same distance in between, and here I mention that this distance, I denote that distance by the letter h. Now the task is to figure out these values. Okay, so if we had the graph, those values will be let's pick a color. Those values will be these points. That is if we had the graph. Okay, but now we don't have the graph. So the task of the task of all these numerical techniques is to figure out some approximate values on this y side. Yellow. So what we are going to do in all these numerical techniques is to figure out an approximate answer for this side. For example, I'm just like randomly putting some numbers, something like this, or something like 4.1, here 9.2, here 15.98, something which is closer to the actual number. It may be higher than the actual number, or it may be lower than the actual number, but we need that to be closer to the actual value. So basically what we end up is going to be something like this. Okay, so at the end what we have is, we have the actual values on the x-axis and the corresponding approximated values on the y-axis. So if we have lot of x values, we can have a lot of approximated values, and we can kind of draw a like a approximated curve for these chosen, I mean calculated values. That's the whole picture of numerical calculations. Okay, so now remember I said these numbers are just approximated values, and to find these approximated y values there are so many techniques. And few weeks ago we learned a very basic technique called Euler's method, and today we are going to learn this Runge Kutta method. Okay, this is actually more accurate than the Euler's method. Accurate in the sense, the values you get from this Runge Kutta method appear much closer to the actual values than if you use the Euler's method. Okay, right. So what is the Runge Kutta method? Now, before going explaining the method, there's one more thing. Now, in almost all these numerical techniques, there is a certain pattern that we adopt. Okay, so first of all, we have this x-axis, and we start from the initial condition. This is x naught, and we already have the y naught as well. Those points are given. Then we get the next point, and we calculate the corresponding y1. This is a calculation, otherwise we did not know this. So to calculate this y value, we use the method. Okay, and then we get the next point. We calculate y2. For that calculation, we use the chosen particular method, and it goes like that. Now, in all these methods, there's another property that we can see. To calculate y1, we need information from the previous step. To calculate y2, we need information from the previous step. Okay, so to calculate y3, we need stuffs from y2, right? So that's also another thing you should kind of keep in mind. Basically, if you are going to calculate, if you calculated the nth value, x nth value and the y nth value, and then to calculate yn plus 1 at xn plus 1, you will need the information in the previous step. So going back like that, uh, we can going back like that, we should understand here, like if you need this, you need this. If you need this, you need the one before that. Likewise, if you go back, you actually have a starting point because these initial conditions were given to you, so you don't need a step before this. That's the starting point which is given, and from this you can calculate y1, and then you can calculate y2, and then y3, y4, and so on. Okay, and then you need a precise stopping point as well. You should say calculate from here up to the given point, like I mean up to a certain pre-specified point. Okay, so the overall idea is you have the differential equation, let's say this one, with the initial conditions. So that is x naught and y naught. X naught is 0, y naught is 0, this is this 0, this is this 0, and then we have an interval, let's say from 0 to, that's the starting point, to 10. Okay, now we have an interval, then you make segments on that interval. That segmentation kind of is on us, like we can separate it into like 2 segments, we can separate it into 5 segments, 7 segments, 10 segments, like that's our choice. And once you segment it, you can name these values x3 and the xnth point, which is 10, and then at each and every point we will calculate the corresponding y value. Okay, so that's the idea. And now let's go to this specific technique of Runge Kutta method. Now, in all these numerical techniques, when they specify the method, what they do is they give you this relationship between yn plus 1 and yn, because we know that's how it goes. If you have all these things and if you have a method, you can get this. Okay, because they are linked with the term before that, before the current one. Okay, so now if you check this one, I'm not going to like go into lot of details about the derivation of this technique, but I'm going to explain you the method. Okay, so the one we are going to learn today is called the classical fourth order Runge Kutta method. There's a second order one as well before this, but this is the one that's commonly used in day-to-day practice. So what we have here is the xn plus 1 term written as xn plus h. What does it mean? That's you have an interval, you have a certain interval, you start from 0 and you have the interval length as h. So this x1 is actually x naught plus h, right? And then you have x2 again length h, so x2 is equal to x1 plus h. Likewise, you have an xn and then xn plus 1 has a gap of h. So basically xn plus 1 is equal to xn plus h. All right. So that's what we have here. And then they give you a way to calculate the yn plus 1 values. And this is the formula to do that. It looks complicated, but you don't have to worry too much about it because we are never going to do all these things by hand in a practical application. We have like this can be like very easily programmed using something like Python. So although it looks like a complicated looking formula, it's just some simple arithmetic that's going around. Okay, so to calculate yn plus 1, so basically let's say if you want to calculate the very, like you have the initial condition x naught and then y naught, and suppose you need to calculate the very first y1. Okay, we will know the x1 value because that's up to us to decide depending on the h. And to calculate y1, all we need is the y value in the previous step, which is y0. And then you have these k1, k2, k3, k4 terms, and they are defined by these 4 values. Okay, so what are those values? You have the h that's known. What is fxy? Fxy is the function in the differential equation. So see, this is the format of the differential equation that we are dealing with. So you have dy by dx equals to fxy. It can have terms of x and y. Okay, but in our case we have a more simplified version, which is 2x. So fxy is just 2x. You don't have a y term in here. Okay, so depending on that formula, we can calculate this value. Right now here in our case it was just 2x. Okay, so to calculate k1, all we need is h f x naught y naught, because see, we are calculating n plus 1th term. In this case we are calculating the y1 term, and for that all we need is the values in the previous term, so y naughts and x naughts. All these terms represent values in the previous term. So accordingly, the value of h, what is h? Say we are segmenting our number line like this, 0 1 2 3 4 and so on. So the distance between these x values is just 1. This is 1. All these distances are 1. Therefore the value of h is 1. You get a 1 here, and this is x naught y naught. So if you substitute it, you get 2 times 0. Okay, this is a very simple formula. I mean, this is not complicated at all, but when the things become more complicated, when you add more and more terms, you will get some non-zero values. Okay, right, so the k1 value is 0. And then K2, you have h f x naught plus h by 2 comma y naught plus k1 by 2. See, all these values are kind of related to each other. So let me erase this one. And now we have again the value of h is 1, and inside you have 0 plus 1 over 2 comma y0 is again 0 because we are dealing with x0 equals 0, y0 is equal to 0. That's given. So you have 0 plus 0 divided by 2 because k1 is also 0. And you get 1 f half comma 0, which is 1. So my function is this times 2 times half because this is fxy, which is 2x. Okay, so that's equal to 1. So k2 is equal to 1. Similarly, you can find k3 and then you can find k4. All these things are linked with each other. Okay, see, to find k2 you need k1, to find k3 you need k2, and likewise. Okay, so you can find k1, k2, k3 and k4 values. And so now you have the values here, here, here and here, and then that means you have the value of y1 plus yn plus 1, which is y1 in our case. So that is equal to y0 plus 1 over 6 k1 2k2 plus 2k3 plus k4. Okay, substitute these values that you found and you get y1. Okay, and this process will be repeated. So you basically start from here, start from a given point x0 y0, and then you have x1, calculate y1. To calculate y1 you need to calculate k1, k2, k3 and k4. Using all these values we calculate y1 according to the formula y1 equals y0 plus 1 over 6, that expression with k values, k1 plus 2k2, k1 plus 2k2 plus 2k3 plus k4. Now we have y1, and then we get x2, that's a known value, and then we need the y2 value. To do that, once again we calculate k1, k2, k3, k4, and then we calculate y2 using y1 plus 1 over 6, the new k values. Same process will be repeated, okay, until you ask the program to stop. So basically we define the stopping place as well. I need to calculate something like calculate this until you reach the x value, let's say 10. Okay, right, so that's the basic idea. Okay, now there are few like fine tuning we should do. Now here I'm going to use another example. For that, instead of taking this as like a large number 10, we will go with the interval 0 to 1. Okay, so the highest point is going to be 1, but I'm going to have some smaller points like this. All right, and the differential equation that I'm going to choose is this one, 7x6. And this becomes an initial value problem when I specify my initial condition like this. Okay, so basically what I have is x naught equals 0, y naught equals 0, and then I'm going to have an interval 0 to 1. All right, 0 to 1, and then I know this value. I know the corresponding y naught value because they were given as initial values, and I need the answer at this point when x is equal to 1. What is the y? Now the thing is, uh, so to do that, what I'm going to do is calculate the value of y with this x using the numerical techniques. Now the thing is, what you should understand is, since this is a very simple differential equation, uh, you can actually solve this one using the analytical techniques we have learned. Okay, so the answer to this differential equation is yx equals x to the power 7. That's the answer, the actual answer, the analytical answer. Uh, and the value of y at 1 is simply equal to 1. So that's the precise answer. There are no errors in this answer. But when we use analytical techniques, when we use numerical techniques, you will see that you are not going to get this one. You will get some value which is closer to 1 but not exactly 1, right? Okay, so my end goal is this, right? Now, how to do this? I mean, how do we set up my problem? So, I have a starting x value which is 0, and the corresponding y0 was again 0. Now, if I just consider this as my interval with the segments, you have 0 here, you have 1 here, I can simply consider this as my h, which is 1. So in one single step, I'm going to reach 1, and then I can calculate y1 accordingly using the Runge Kutta method, Runge Kutta method. How do we do that? This is written as y1 equals to y0 over 1 over 6 k1 plus 2k2 plus 2k3 plus k4. Did I write that correctly? Yes. And we have some formulas to calculate the values of k1, k2, k3 and k4 depending on the values in the previous step. That's this one, x1. Okay, so we can find an answer here, and we'll see what that is. Now here, if you just search for some Runge Kutta online solvers, just Google it, you will get a lot of online solvers. I found this to be helpful. Okay, so now first what I did was I typed the differential equation. It's 7x to the power 6. That's the differential equation we are dealing with. 7x to the power 6. And then initial condition, initial x, that's x naught, initial y, y naught. Point of approximation, that's the target point. And now the step size. and calculate that. See, you get 1.23958. So basically, you can see the calculation here. This is the 0th step, xn. So substitute n in here. So this becomes x naught and y naught, 0, 0. That's the initial conditions we substituted. Using those values, it calculates k1, k2, k3, and k4. Using those k1, k2, k3, and k4, they calculate the y-nth value, y1 value. Okay, so that's going to be 1.23958. But the actual answer, as we know the real analytical value, we can kind of compare it with the actual answer. The actual answer should be 1, right? But what I get is 1.2359. Okay, so let's draw these curves. This is another good tool to draw the curves. Okay, Desmos calculator, just Google Desmos, and the very first link you will get have this graphing calculator. It's again an online free tool. So if you want to draw this curve, let me zoom out. So this is the solution curve. Now remember, this is the solution. Okay, and my differential equation was this one. I'm not drawing this one. I'm not drawing the right hand side of the differential equation, but I drew the solution curve. Okay, right. Now also we can plot the points. So at 1, you will see that it is equal to 1. Okay, that's the actual point. That's 1 comma 1, right? So that's the let's say, let me name it as A. That's the actual point, right? But now what I got was 1 comma, that's my x value. So the x value is 1, right? x1 is 1, and the corresponding y1 is, using the Runge Kutta method, y1 value is this one. Okay, so that's going to be a little higher than the actual value. So let's name it as b. Okay, right. Now we are going to refine it a little further. So once again, our end goal should be to calculate this one, y value at 1. Okay, let's get the interval. I have the interval x naught and y naught. I know this one and I know this one because they are the initial conditions, initial values, and I need x equals 1 and the corresponding y. Now earlier I just considered this big interval as the entire segment, but now what I'm going to do is I'm going to cut it in half, and I'm going to introduce a new point here. Let's call it as x1 because that's the number after 0. Okay, I'm not talking about 1 and this one and this one are two different, well, I mean represent two different ideas. So in the middle means 0.5, and now y1 for the 0.5, and this x becomes my x2 and the y2. Okay, so first we need to calculate this point, y1 value, using y0, 1 over 6, k1, 2k2, 2k3, plus K4 with the K1, K2, K3 and K4 calculated according to the given formula. Get this one. So now we have x1 and y1, and then you calculate the y2 using this. Now we have y1 here, which was calculated in the previous step, right? So that's the plan. Cut this in half. So my h is now 0.5. Okay. So now you have two segments in this interval, and still the end goal is to identify the value when x is equal to 1. And to reach this, I go with two steps. But earlier, we used a single step. So here, the value of h, or the interval size, or you call it as the mesh size, or you can call it as the interval size. Mesh is because if you are thinking about a two-dimensional case, you are going to construct a thing like this, which is known as a mesh. So this mesh size was 1, and here in the more refined case, the mesh size was 0.5. Okay, so now let's see what happens. Now I'm going to have still the point of approximation is 1. Initial conditions are the same. Step size or the mesh size is 0.5 now. See what you get. Now here, I think by default, this sets the decimals to 2, but that's not going to be enough. Just increase it at least up to 5. Okay. Now the step size, when you increase the step size, you have 2 points. See, you start from this. Let me get a screenshot of this one. Now what you have is, you started from x naught equals 0, y naught equals 0. See, this is xn and this is yn, and the value of n is given here. So x naught equals 0, y naught equals 0. Calculated the corresponding k values using these numbers, and then used this formula to calculate y1. And now this refers to the case where n is equal to 1. So this becomes x1 and this becomes y1. So x1 is 0.5. We already knew that. And the suitable y1 is 0.009 something. Okay. And then we calculated the k1, k2, k3, k4 values using these numbers. And now we have the x2 and we have the x1 and y1. Okay. We wanted the x2 value, which we knew. And that's this is x2, which is 1. This is the value of n, and now this becomes the y2 value. Okay, so y2 will become 1.01742, right? So let's see what's that number in the graph. 1 comma this value, let's label it as c. See, it's getting closer. Okay, it's getting closer. Let me zoom in. It's still not exactly the same, but it's getting closer, right? You have a gap, but it's getting closer. But if you zoom out, you kind of don't see much of a difference. So that's also another thing we should be careful about. Whether we are zooming in or whether we are zooming out depends on the problem and the meaning of these distances. Okay, say for example, if you are measuring something in a, like some distance between two planets, and if one square length represent, like let's say some like 1 or 2 miles, that's okay, right? If you are measuring planetary distances that is in the range of millions of miles, and a difference of 1 or 2 miles doesn't make any difference. But now suppose you are measuring the distance between two atoms, and if this length refers to like 1 centimeter, 1 centimeter in the like micro scale is a huge gap. So this is not enough, you have to make it more precise. How do we do that? Let's make this interval, like let's introduce more intervals. We have again x naught and y naught, and the start, the end point, x end 1, y end is the one we need. So earlier I had 2, now make it 4. Okay, so my gap is going to be 0.25. That's basically the half of 0.5. Now my x values will have x1 is equal to 0.25, and then x2 is equal to 0.5, x3 is equal to 0.75, and finally x4 is equal to 1. And now how about y1? How do we calculate y1? Use the formula. We have y1 equals y0 plus 1 over 6 k1 to k2 to k3 k4. Calculate k1, k2, k3, k4 using these values, initial conditions, and now we have y1. And then how about y2? You have y1 with this formula. Calculate these k1 values using x1 and y1, and then you have y2. And y3 we calculate using y2 values and the suitable case in this step. That's y3. And finally we get y4 using the values obtained in this step. So we need this one, this one, this one, and finally this one. All right, so that's for the step size 0.25. Let's see about that. 0.25. Give me a second. Okay, so that is 1.0013. Let's take this one. Now see, we have the n equals 0, so this becomes x naught and y naught given initial conditions. Using those values, calculated the k1 up to k4, and then we have the y1 value, that's n plus 1. N is 0 in this row, so that is the y1 we have at x1. This is x1 and this is the corresponding y1, that is this number. Okay, and then we have x2, which is this one, and then use these values using this step. Calculate k1, new k1, k2, k3, k4 values using x1 to calculate the y2, and that is this y2 which appears in here. All right, and then let me pick a color, blue. Now we have n equals 3, that is this step 7 5. Use the k values, calculate the k values using the second step, n equals 2, you get y equals 3. Okay, that's the new y value, which is the one number in here. Do the same thing, we calculate y4 here, which is the number we need. Okay, that's 1.10113. So let's see that in the picture. That's again, remember, that's again hold on. So that's again this one. X is the value of x is 1. We are always at this endpoint. X is 1, y is the value we calculated. Okay, so in my coordinate pair on the graph, I'm going to have 1 and the new number. Okay, let's label it as D. Hold on, I'm sorry. So give me a second, I'm getting a call. All right, so now D is pretty much accurate, right? But still, if you zoom in, see, we are still a bit away from the value of A. Now, none of these numerical techniques are will not give the exact answer most of the times. Okay, so we have to determine where we mark the endpoint, which one is okay for us. I will explain that in a bit, but let's do one more calculation. If you want to make it more precise, let's make it like, let's divide the, now in the previous case the value of h is 0.25, so let's 0.25, let's divide that by 2, you get 0.125, and then you get this, so you have x0 1 2 3 4 5 6 7 8 values. Okay, x8 will give you 1, y8 should give you the numerical answer at x equals 1. Okay, so let's see what that is. This is 1 to 5. It will take some time. See, now it is way better. Okay, let me have that too. And I will label it as E. All right, so let's zoom in. Okay, so E is the last one. A is the actual one. Okay, see, it's very close to the value of A, the actual answer, right? But still, it can be improved. Okay, if you like divide h again, you will get a more closer value to a. See, now if you zoom in into a suitable scale, you have a big gap between d and e, but if you zoom out, you don't see that difference anymore. So it totally depends on the scale you need this problem to work on. All right, so now that's the idea of this Runge Kutta method. Now, before moving on to the final section of this chapter, I want to assign you a homework. Okay, so your homework will be to do this analysis for the function this one, dy by dx equals 8x7. So the initial condition is y0 x0, y0 equals to 0. Okay, so this is going to be your homework. This is my initial value problem, and what I want you to do is uh, install a screen recorder to your computer. One that I would suggest is this one, Screen Rec app. It is a free software that you can install, and you can record your screen through this app. It's a free app. And worst case, if you don't want to install this one, just get your phone, hold it from one hand, and record what you are doing on the computer. And what I need is just a 5-minute video of you typing all these values and calculating all these numbers. I want you to record you doing that. Okay, not pictures, but you should record it with some voice over so that I know it's you who are doing the work. Just try to do like just try to speak at least a few sentences so that I know it's you, not someone else, not that you are using your friend's video. Okay, so your homework is do this analysis for the function, this one, for the initial value problem, this. Now actually the answer is going to be yx is equal to x to the power 8. Okay, so draw the graph, this one, in Desmos. Start with that. You will have a graph on the Desmos. Hold on, sorry. You will have a graph on the Desmos, and then for all these step sizes that we worked with, step size h equals 1, do the Runge Kutta method using this online tool and calculate the y1, and then make it half, that's 0.5, then calculate y1 again. And when you calculate this y1, plot that point. When you calculate this y1, plot that point. Make it half, 0.25, calculate y1, plot this point, x1 comma y1. Make it half again, 0.125, plot that point. And while you are doing it, record what you do, and with a voice over. You have to speak at least a few sentences so that I know for sure that it's you. Okay, so that's going to be your homework for this week. Just upload that video in this week 10 homework one. There is a place to upload the video. Okay, so to get the video, either you can install a screen recorder, or else you can just use your phone on one hand and do the work using the other hand. Okay, right. So that's about the homework. Now there are a few more things I need to tell you about this Runge Kutta method. Now here, when I was doing this technique, okay, I kind of compared it with the actual answer, right? That's what we did. But we have a problem here. Now, let me zoom it in, make it go away. You have all these points, okay? The issue we are going to have is in a practical situation. Remember, I said if we are solving a differential equation like this, in a practical scenario, we will not have a precise way of getting the analytical answer. So that's going to be a problem. Okay, so now here I measured the accuracy of this method just by comparing it with A. And what is A? A is the actual answer, right? But in reality, we don't have that. Okay, so what we are going to have is not this curve, not A. Okay, we are going to calculate a bunch of points using the technique measured at the same point. Okay, so let's take the first 2 points. B and C. I'm not sure why it shows E, but anyway, so let's take these 2 points B and C. Now what we can do is to measure the accuracy, to see whether it is accurate or not. What we can do is pick an H value. Okay, pick an H value and calculate the answer you need. It was 1.2359, this one. Half that H, calculate the Y value at the same X. Okay, you will get a different answer. So B and C. You can measure the distance between these 2 points. Okay, just get the absolute value of the 2 distances. Okay, so Y from the let's call this as what do I call? Let's name H naught as 1, H1 as 0.5, H2 as 0.25, H3 as 0.125. So get the Y value you obtained using H naught and subtract it from the Y value you obtained with H1. You will get a number. Okay, and then you get the Y value. So let's do that one. Let me take these 2 numbers. So that's going to be this one. Let's get the calculator. This minus this one is equal to 0.22. That was 0.22. Okay, now in these numerical calculations we defined a value called the tolerance level. Okay, let's name it with the letter epsilon. Let's name it with the letter epsilon. So this is called a tolerance level. That's kind of a measurement of the accuracy that we need. Suppose the tolerance is 0.01. 0.001. Okay, so if this number is larger than the tolerance, we make it half again. We make this value half again and calculate the y at the new h2 and compare it with the value in the previous one. Okay, so that's basically get rid of this one and now use it with this one. Okay, so C and D. Let's zoom in. We have C and D. Measure the distance between these two guys. So that's going to be, we always get the absolute value to get rid of the negative values. This one minus, what I mean by the negative values is you can subtract this from this or this from this. Both are considered as the same thing. We just need the distance between the two. That's going to be 0.01. See, the gap decreases. Okay, but still it's greater than the tolerance. So we half it again. And now subtract the value you get from the new h value with the previous h value. Okay, now these are not consecutive steps in the same Runge Kutta calculation. These are separate Runge Kutta calculations, Runge Kutta calculations. Okay, y values obtained using this step size, and these are the y values obtained using this step size, and this is the y value you obtain using this step size. All right, so now we need the measurement between this and this, and that is D and E. Let's zoom in. Where did it go? Okay, so what I have is this one. This gap, I need to measure that. 1 point, this one, minus this one. See, it's 0.01. It's again like somewhat similar. Okay. Yeah, it's similar. But if you consider a few more, two zeros are there. Yes, not similar, not at all similar. It's very much smaller than this one. Okay, so it kind of have reached the tolerance. Let me increase the tolerance a bit. So let's go with 0.005. Okay, now here still it is greater than the tolerance. Now it is less than the tolerance, which is 0.005. Okay, now we can say that, okay, now the solution kind of converges into a specific value, and we consider this as a good enough answer with respect to our tolerance. That's how we make sure that our solution is okay, right? Because we don't have an actual place to compare, because we don't have an analytical answer, we just have to deal with what we have got. What we have is the result from the numerical techniques, and therefore what we do is we reduce the step size, evaluate the answer at the same x point, and we compare them and see whether this gap keeps reducing, and after it reach a certain point, a predefined tolerance, we say that, okay, now this step size is all right and we can accept this as a suitable answer. The main idea is it kind of we kind of consider it as a converging sequence, as we haven't done the idea of sequences yet. I mean, we are not covering the sequence in this course, but it's sort of a converging sequence, and a property of a converging sequence is that when it reaches the converging points, the gap between the consecutive terms will reduce. So that's the property we see in between these numbers. So if this gap between the different step sizes keep on reducing, and if it reaches a certain predefined tolerance level, we accept that final answer. Okay, right. So that's all about Runge Kutta method. And there are various modifications to this method, and even for this tolerance, we sometimes consider a thing called relative tolerance, which is more accurate. And also, there are few more variations for this Runge Kutta method. This method itself is called the fourth order Runge Kutta method, and sometimes there is a thing called RK45. So that's kind of combining the fourth order and the fifth order Runge Kutta. So there are various types of the same sort of technique you can expect when it comes to numerical techniques. And this paragraph above this one is for the second order Runge Kutta method, still the same criteria. Okay, right. So that's pretty much it about the lesson for today. I know it's a heavy lesson. Please go through this video slowly and do the homework that I assigned. Now for the homework, you don't have to do this error analysis part. You just need to get the graph as I explained earlier. Okay, right. So, and feel free to let me know if you have any questions. Thank you for joining our online class.